Name is Arjun, and this is Physics 2212 Lab 5. Now, before we start this lab, let's review the concepts that we will use in this experiment. One is the concept of magnetic fields. Second is the concept of magnetic fields due to bar magnets. Third is Lenz's law and Faraday's law. And the concept that a change in magnetic flux always creates a magnetic field and an electric field. Now let's move on to the experiment. The experiment involved me dropping a magnet down a tube, aluminum foil tube, and measuring the time for which the magnet was inside the tube. Now, the for which the magnet was inside the tube was measured by taking the timestamp of the point at which the magnet entered the tube and the timestamp of the magnet at which the magnet exited the tube, and finding the difference between the two. Tracker was used for precise measurements. But why? So a question to be asked is, why are we doing this experiment? We're doing this experiment because we know that magnetic flux changes causes electric field in the aluminum foil, and that electric field induces a magnetic field which opposes the direction of movement of the original magnet falling, and that's why the magnet is slowed down as compared to when we see it in without falling in free fall. Here are results and the constant values from the experiment. Length of tube, width of foil, inner radius. These were used in the simulation, as I'll explain later. Left is time for going in, for at which the magnet went in. The right is timestamp at which the magnet came out. The total time is just a difference between the two, and we found out that the average time for which the magnet was inside the tube was 3.551 seconds. These are in four significant figures, primarily because of the software used, which was Tracker. Also, the video was recorded in slow mo for a better visualization. Some questions regarding the experiment: why can a ferrous tube not be used? Primarily because they are magnetic in nature and they will attract the magnet towards themselves, and therefore the magnet will not really fall. Second question: what happens when the magnet is falling? As I just explained earlier, the magnet slows down and it is falling with uh, different kinds of acceleration, because as it falls, the magnetic flux changes, and the magnetic field and the magnetic forces due to the aluminum tube also change. This is contrasted to a magnet falling in free space where there's just uniform constant acceleration because of the gravitational force of Earth. Note, magnetic field of Earth does not play that huge a role because it's very small. Now we'll move on to the simulation part of the experiment. So I'll move on to the code first. Here is the code for the experiment. As you can see, um, so I won't go through all of it, but this is creating the aluminum foil. This is creating the bar magnet. These are just for VPython and our calculations. Initial conditions. Um, this is creating a function for the magnetic field calculations, magnetic flux calculations through one ring, and then finally the simulation loop that loops across the movement of the bar magnet as it falls. And we're done. Let's run this program and see what we get. This is the magnet falling. Here's a graph. So the if you could see the red and the blue colors, they were corresponding to magnetic poles. The north pole was the blue color, and the south pole was the red color. Also, the time taken was 2.776 seconds for the thing, and the graph is seen over here. Coming back to the presentation, what happens to dynamics of the system when you flip the magnet? When you flip the magnet, the field remains the same, but the poles switch. So the time should remain the same, but time of descent, that is, but the directions of the poles should change, so the color should change. What happens when you compare real world data and the computational data? Real world data we had around 3.551 seconds, and computational data we got 2.7 seconds. There is a difference. This difference can be attributed to the friction experienced by the real magnet falling in the real experiment, the frictional experience in the form of the magnet turning sideways and there's therefore always touching the sides of the aluminum foil as it fell down. This I saw in my experiment. Now, this friction could be attributed to the increased time. So, you could account for that in the simulation when you're building a better simulation next time. Some further questions. What if the resistivity of the conductor were reduced as close as possible to zero? If that were to happen, then the magnetic flux loss or the magnetic field loss, induced field loss, would be minimized, and therefore the magnet would reach its optimal magnetic field at a faster rate, and therefore the magnet should fall down faster. This leading to a decrease in total increase in total time. I mean, it should fall slower. What if holes or slots were cut into the tube? If holes and slots were cut into the tube, the magnet would fall down faster. This is because the holes and slots would disrupt the magnetic fields being created by the magnet aluminum foil, and therefore it won't be as strong. It's like, if you think about it, if you remove one loop, the magnetic field reduces because it's loop wise, and therefore the total fall time should increase were we to have holes or slots cut into the tube. And that's all I had. Thank you.